All right, let's go through this. So if we want to figure out the position at a given time, we're going to want to use this formula here. Okay, and this formula applies, well, simple harmonic motion, and we started it out at its maximum position. So that's good. So this formula applies. So amplitude. So amplitude is how far I initially started it out, right? So amplitude is 1 meter. Okay. The period of motion and angular frequency. Well, omega is probably the easiest one to do starting out. That's square root of k over m. Well, so this is square root of 1,000 over 10. Everything's in SI units, so that's just 10. The units are seconds to the minus 1. Okay? So square root of 100, which is 10. Period is 2 pi over omega. And so that is 2 pi over 10 seconds, which is pi over 5 seconds. For part B, I'm just going to use this formula, noticing that this is omega, the W thing. So 1 meter, so X is 1 meter, that's the amplitude, times cosine of 10 seconds to the minus 1 times 0.5 seconds. So this is 1 meter cosine of 5, that's 5 radians. And I had to use, when I used a calculator, I wrote, I had to convert, I didn't have a radian mode, so I converted this to degrees by just multiplying by 180 divided by pi. Anyway, what I ended up with was 0.284 meters.
If you were doing it that long way, would you take 1 meter cosine of 10 and then time it by 0.5?
1 meter cosine, no. The 10 and the 0.5 have to be multiplied together before I take the cosine.
Okay, see that's
Have to be multiplied in the cosine.
Okay.
Okay. Yeah, there'll be a big difference. Make sense?
Can you also have done for the period 2 pi times the square root of m over k?
2 pi times the square root of, yeah, should be the same thing, right?
I got the same answer, but I got 62.8 for when I did it the other way, and when I did it that way, I got 0.628. So.
Oh, all right. So this is square root of m over k is 1/10, right?
Yeah.
So t is 2 pi times the square root of m over k. 2 pi over 10 is pi over 5.
Yeah. I just did 10 instead of 1 over 10.
Okay, oh, one more thing, just to make sure that we're all clear on, to remember our springs. So at this time, C, at this time, what is the speed? And we'll do this one together. The speed of the mass. Question mark. So So how do you think we should go about that one? You know how much a spring is stretched, don't you?
Yeah.
Do you know how much energy you started out with? Yeah. So on this one, we can use conservation of energy. And once we know the position of how much the spring is stretched, you can always figure out what the speed is. And that's because this is a nice conservative system. The kinetic energy plus the potential energy is going to be a constant. So let's go ahead and check this out. So the total energy of the system is the potential energy plus the kinetic energy, and that's equal to a constant. So that doesn't change. If I pull this out 1 meter and let it go, at 1 meter it's a rest, right? So I know how much energy is in the system if I do that. So initially, when I moved it out by 1 meter, what's the kinetic energy?
0.
0, because it's not moving, right? What's the potential energy?
1/2.
1/2 K.
So potential energy is always 1/2 K
KD.
x squared, right?
Yeah.
Or d squared, which is the distance the spring is stretched. If I start out at x equals 0, then that would be the same as x squared, right?
Mm-hmm.
So, and then kinetic energy is 0. And what's my initial x position?
1 meter.
So that'd be the a squared, right? So I could write this as 1/2 times 1,000 newtons per meter times 1 meter squared. And so if I do that, 500 joules, right? Makes sense? That's the total energy is, so E is 500 joules. So that'll have to be the same amount of energy at any time, because we're not having friction or anything like that starts robbing energy. Oh, I'll leave that 0.28. So when this is at x is equal to 0.284 meters, I know what the total energy is, still 500 joules, right? Okay, and I know what the potential energy is because I know the distance. So I also know the kinetic energy, don't I? So I can get the speed. So let's take 500 joules, that's the total energy. We'll set that equal to the potential energy. So 1/2 kx squared. That'll be plus the kinetic energy, 1/2 mv squared. So plug in x equals 0.28 meters into there. So 500 joules. I'm going to bring this over to here. Minus 1/2 kx squared is 1/2 mv squared. I'm actually going to do a little solving before I plug in numbers. I'm going to multiply this whole equation by 2. That'd give me 1,000 joules. Minus kx squared is mv squared. I'm going to divide that whole equation by m. Like that, right? Then I'm going to take the square root of both sides to get v. So square root of 1,000 joules over m minus k x squared over m is equal to v. This m is 10, right? K is 1,000, m 10 here. So I would write this, and then x was the 0.284. So I'd have that 10 or 100 meters squared per second squared minus, this is 100 x squared, 100 seconds to the minus 2 times x squared, which is 0.284 meters squared. So take 100 minus 100 times 0.284 squared. Okay. When you do that, what do you get?
92.16.
92.16. Yep. Are you sure?
Oh, no, I didn't square root it.
Okay, good.
9.6.
Okay, is that what everyone got? Okay, and then one last thing. I'm just going to show you a plot of what these things look like. If I were to look at the x position as a function of time, it would start out at the amplitude, A. Cosine starts out at its maximum value at the 0 point. And it would oscillate back and forth like this. The distance between these peaks, this would be the time t, the period. Where I'm back above one of the peaks. Period here. Now, if I were to overlay that on a plot of the velocity, velocity would start at 0, where it's at its maximum amplitude, and it would be just be, so this would be velocity as a function of time, kind of be offset like that. And the total energy here would be constant. All right, I'll let you guys go. So. Back to the assignment.